Hello everyone, and welcome to this third supplementary part of Lecture 13. What we'll be doing here is applying some of the machinery that we talked about in Part 1 to some really cool stuff in regards to philosophy of mathematics and talking about the nature of infinity. So in order to kind of lead up to it, let's talk about some interesting sets that we might come across. So the first one is this set we'll express with this funny little n, and it's this set of the naturals. The naturals are any ordinary whole number that we tend to use for counting or ordering. So it's the set of 0, 1, 2, 3, 4, etc., etc. So they're all positive, they're all whole, and they're the ordinary ones we would use for counting. Notably, it starts with 0. So some use natural to exclude 0 and whole number to include it. Others use whole number to exclude 0 and natural to include it. I'm going to just use natural here. So this little n is the set of the naturals. What's notable is it's pretty clear there's an infinite number of natural numbers. So there's going to be a whole lot of them. Now, that's our first little important set n, the naturals. We can introduce set z, or z if you're feeling British. Right? Z is the set of the integers. And an integer is any natural number, including 0, or a negative non-natural, or a non-zero natural number. So, in effect, it's all the naturals and their negations, their negative ones. So you've got 0, 1, 2, 3, counting up infinitely, and 0, and then negative 1, negative 2, negative 3, so on, infinitely downwards. Right? Notably, they're all going to be whole. So all of the integers are the wholes, or the whole numbers, starting at 0, going up, and going down. So that's our set Z. Right? N, to go back, N was all the naturals, so 0 counting in whole numbers upwards. Z is 0 counting downwards and upwards. So N and Z. Cool. Now another important set we can come across is Q. And Q is the rationals. Now we can write it in a slightly fancy way, right? Or we can kind of express the rationals as basically any number that can be expressed as the quotient of fraction P over Q of two integers. Notably, of course, Q is non-zero. Right? So this will include all the whole numbers, but it will also include anything that we can express as a fraction with integers, whole integers here. Now, what's really nice is that Q can be expressed maybe equal to 1, so this gives us all the rational numbers, but importantly, of course, every integer isn't going to be a rational number because it's not necessarily going to be whole. So again, nice little thing. So what's neat is the decimal expansions of a rational number always either terminate with a finite number of digits, or they begin to repeat the same kind of finite number of digits over and over. And this actually is going to be true in base 10, binary, hexadecimal, any integer base. It's kind of cool. So for example, like 1 over 3 is a rational number because what you get is just 0.3 and then 3 repeating infinitely. Right? So again, any kind of number we're going to get that we can express as a fraction that either terminates after a finite number of digits or starts to repeat the same finite sequence of digits over and over. So that's Q. Okay. Now, the last one we want to talk about is really interesting, and that's this set of the reals. So real we can think of as basically just as a value you can represent in a distance on the number line. The reals are the rational numbers, so the ones we can express with fraction that we've defined just as we did a second ago, that's going to either terminate or begins to repeat, plus the irrationals. So that's any number that cannot be expressed as a quotient or fraction, P over Q of two integers, Q is non-zero. So a real number is any number that's rational or irrational. So for example, the square root of 2 looks like a very good one. It's an irrational number. Pi is an irrational number. Right? It's not something you can express as a fraction. It doesn't have this kind of repeating bit that will constantly go on. It looks like it just keeps varying what digit it's displaying as we go. So those are four important sets, all just thinking about numbers, right? We have the naturals, we have the integers, we have the rationals, and we have the reals, which are the rationals plus the irrationals. And again, we can express them as n, z, q, and r. So these are pretty typical ways to express them. These are the ways to pick out these sets. So these are just sets of some different ways to think about numbers, and they're interesting in and of themselves. What's really interesting is when we start to think about how big these sets are. So it's pretty clear that they're, just to coin a phrase, real fucking big. But of course, the question is, just how big are they? Right? In particular, we might start to wonder, what's the relationship between some of them? Is any of them bigger than the others? Right? So what do we think? We might wonder, like, hey, are the naturals smaller in some sense than the integers? It seems like they should be, because, right, we can basically, like, look, they're just half, right? This one goes down, and this one just is the up part. Similarly, like, the rationals look like there should be more than what's going on with the naturals or the integers. And don't even get me started on the reals, right? So it looks like there ought to be some kind of hierarchy, right? This one should be big, but this one should be bigger and even bigger. So how do we make sense of this? Is that right? So let's ask ourselves something kind of related. And let's ask, is the set of natural numbers bigger than the set of even natural numbers? So let's just define a set. We'll just introduce E. So E is the set of everything that's an even natural number. Right? Does N, so the set of all naturals, have a bigger cardinality than E? Well, it seems at least intuitively like it should, right? So N should be bigger, because N doesn't just include the evens, it includes the odds too. Right? So N has 0, 1, 2, 3, right, 4, etc. Whereas E just has 0, 2, 4, blah, 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 blah. So it should be, like, intuitively, people think that N's got a bigger cardinality. But here's the weird thing. It doesn't. In fact, the even naturals can be mapped one-to-one with the naturals. We can give an isomorphism. And this is the creepy thing. That means they have the same cardinality. So N and E, my set has of just all the even natural numbers, is going to have the same exact cardinality. And how would we do the mapping? Right? Well, it's fairly easy. Right? We have 0 mapped to itself. We have 1 mapped to 2. Right? 2 mapped to 4. You can see how this will go. Right? And this is actually really kind of interesting. This is a key characteristic of infinite sets. The members of any infinite set can be paired up one-to-one with the members of some of its proper subsets. So here's right, this is really cool. So what we really mean here is we talk about denumerability. So an infinite set is denumerable if and only if it can be mapped one-to-one with the set of naturals. What's really interesting is that there are an infinite number of infinite sets that are denumerable. But some kind of key ones include set Z that we mentioned earlier, the odd naturals, the even naturals, the perfect squares, the set of all grammatically correct English sentences, the set of all grammatically correct Dutch sentences, the set of all German sentences, though that one's a bit ugly with regards to cardinality. So really all we have to do is just give a mapping, right? Some kind of mapping. And it's fairly easy. We can even do it with the set of TFL sentences. In fact, we did it. Right? In lecture 12, we mentioned a kind of tool, or actually it was in lecture 11, I guess, where we mentioned a way we can think about length of TFL sentences and giving them a cardinality, which then maps them to a natural, so any TFL sentence is guaranteed to go in hand with the set of naturals. It's going to be denumerable. That's really creepy and really cool. So it turns out that when we're playing around with lots of our infinite sets, they're all going to turn out to be denumerable. That is, they're going to have the same size of infinity. That's neat. So there aren't more naturals than there are even naturals. There's the same number. And there's the same number of odd naturals as there are evens, or that there are just naturals in general. So that's kind of neat. And actually, we can extend the weirdness a little bit further. So let me introduce you to Hilbert's Hotel. So Hilbert's Hotel is a kind of interesting little thought experiment introduced by a mathematician to think about how we can play around with this and to kind of help us get a grip on this notion about denumerability. So Hilbert's Hotel has a countably infinite number of rooms, and these rooms are occupied by a countably infinite number of guests. So, right, countably infinite number of rooms, so number of rooms that can be mapped, right, to our set N, right, and a countably infinite number of guests who are occupying the various rooms. Okay, so let's suppose that a new guest arrives and wants to check in. So there's a guest in every room. A new guest arrives, wants to check in. Well, is it possible to accommodate them? Now, intuitively, we might think, no, right? Because there's supposed to be a guest in every room, right? There's an infinite number of rooms, sure, but there's an infinite number of guests, too, and each room is occupied by a guest. So we couldn't get the new one, but we can. Here's what we do. What we do is we perform an isomorphic mapping. We have everyone who's in a room move along to the next room. So if you're in room 1, you move to 2. If you're in 2, you move to 3. If you're in 3, you move to 4, so on. Now this will involve an infinite number of people moving one room along, but of course, everybody does it, and now we've got a free room. The first room will be free. And in fact, we can repeat this. Not only can Hilbert's Hotel accommodate an extra guest, even though there was someone in every room, for any finite number n of new guests, you can just repeat this same process. So the hotel could actually, despite the fact that there's a guest in every room, accommodate any finite number of new guests. Of course, that's a finite number. We're interested in the big numbers. So what happens when a countably infinite number of new guests arrive? So that is, a number of guests equal to the naturals show up. Well, it's going to be a hell of a time at the check-in desk, but we might wonder, could we accommodate them too? Is there some way we can move the guests around that are already in the hotel to accommodate our countably infinite number of new guests? I mean, unsurprisingly, you can already guess, the answer is going to be yes. So here's how we do it. There's a lot of different ways we can actually do this, but the easiest one is basically just, cool, whatever room number you're in, just move to the room 2n. So if you're in room 1, move to 2. If you're in 2, move to 4. If you're in 3, move to 6. And note what this will do. This will free up countably infinite rooms, namely all the odd rooms. And this can then be accommodated by our new countably infinite number of guests. So what we've basically done is we've just fit a countable infinite number of new things into the countably infinite space that we already had. And note also, this is the mapping that shows us then how we can get the evens mapped back to the naturals. So what's really cool, right, is this sort of Hilbert Hotel-y kind of stuff is showing us that when we're playing with countable infinities, right, this denumerable infinities, we've got a lot of space. In that basic process, we can count any number of finite new individuals by just simply having people move along and finding space at the beginning. Or if we want to add a countably infinite new number of individuals, again, we just do this sort of mapping, and it opens up a countably infinite number of free rooms. And of course, we're talking about this in terms of a hotel, but it doesn't have to be a hotel, right? It's really just mapping places in a function. And this is really cool because now we're thinking about, like, well, it turns out that n and z And a lot of the ones we can kind of get from it are all going to be the same size, which is cool because we can perform this kind of mapping back to n. So this is sometimes called the Hotel paradox, or Hilbert's Hotel paradox. And it's a paradox in the sense that it's strongly counterintuitive. It feels like a bunch of these sets should be bigger, should have a greater cardinality, but they don't. And it's in fact provably true. So what's interesting is it also kind of shows that when we're thinking about hotels with infinitely many rooms, something like there's a guest in every room and no more guests can be accommodated aren't equivalent. Right? Because we can have a guest in every room, but we can still accommodate more guests and give them their own room because we've got infinite rooms to play around with, even if we have infinite numbers of guests. So very cool. But of course, right, so far we've sort of suggested that everything's going to be at the same, like there's one kind of grade of infinity. Everything's going to basically come down to the same cardinality as n. But is that true? Are all of them going to be able, are all infinities denumerable? Well, let's think about it. Let's talk about Q first again, right? Remember, Q is the numbers that can be expressed as fractions. And Q, interestingly, is also denumerable. And to do this, what we can do is actually kind of write a little mapping. So we can start in the corner with 1 over 1. We can put 1 over 2, 1 over 3, 1 over 4, listing along. And listing all the numerals down, we generate all the fractions as we go through. Now, as we go along here, what we're effectively getting is a mapping. Now, the red ones we can skip because they're already mapped. But again, this is a way we can kind of generate a mapping of all of the things that are in set Q back to n. So in fact, right, n, z, q, all denumerable, really reinforcing the idea that maybe there's just the one kind of degree of infinity. But here's the really cool thing. There's no way to construct a one-to-one mapping from the rationals, the R to n. Right? And to see why, let's consider just a small part of what we have in the reals. So all we're going to do is consider the reals between 0 and 1. So right, remember, there's a whole lot more. So there's all the reals in between 1 and 2, and there's all the ones between 0 and 8 billion. Right? There's a whole lot of reals. And let's just think about the real numbers between 0 and 1. And now note, right, with regards to these, remember what the reals are. So they're the numbers that are going to include all of the other ones, as well as numbers that can't be expressed just as a straight fraction, that then get either terminating in a single digit just repeating, or some sequence of digits that just cycles back. Right? So suppose what we do is we just write down an infinite number, a countably infinite number, of these reals between 0 and 1. So we start with a decimal place, so there's 0 point blah, 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 and we write down some list of them, a countably infinite list of them. And it doesn't really matter what the list looks like. I've done a little jokey one here, but all that matters is we just do it. And we're going to construct a proposed pairing, and we're going to show that it cannot, no matter how many you write down, get even just the reals in between 0 and 1. So we do our little listing, right? And we've got a mapping between all the naturals over here and our randomly generated reals between 0 and 1. And we'll again allow them to be whatever we like. Now let's suppose we write them down in a grid. Right? And we order them in this grid this way. Right? So here's our first one, here's our second one, here's our third one, fourth one, fifth one. And again, imagine this goes down a countably infinite number of spots, and these can go on infinitely as well. So these can be countably infinitely long. Right? They just keep going, they don't end. Never terminate, don't repeat the same cycles, they don't have a single digit that just constantly repeated, like 1 over 3 or something like that, right? So, cool. Okay. And again, what we've done is we've basically got a countably infinite number over here. So this is all the naturals. And these are our randomly generated reals between 0 and 1. Now, cool. Let's just look at this grid. And take the grid, and let's look at this number. So what we're going to do is we're going to construct a new number. And we're going to construct a new number by taking the first digit of the number that we've assigned to 1, and we're going to add 1 to it. And we're going to then take our second digit is going to be the second digit of the number assigned to 2, and we're going to add 1. And our third digit, we're going to make the third digit of our new number, whatever the third digit is for the number assigned to 3, and add 1. And the fourth digit of our new number is going to be the fourth digit of number 4, and we're going to add 1. And so on and so on. We're going to do this all the way down, right? Because remember, this extends countably infinitely downwards, because we've got all of the naturals, all of the natural numbers here, and for each one of those there's going to be a new, like a randomly generated, we don't really care what it is, new real between 0 and 1. And what we're doing is we're picking out this diagonal. From this diagonal, we're going to take this digit, add 1. So, looking at it in this case, applying the function, what we get is this number. So number 0.24680, right? It's going to keep going. Now here's the cool thing. This number, whatever it is guaranteed to not be on my list. Now why is it guaranteed to not be on my list? No matter how we generate these ones, no matter how long this goes, again, remember this is countably infinite, there's going to be a different one for every one. The number I generated using the function I just defined is guaranteed to not be anywhere on my countably infinitely long list. So here's why. Right? For any number n, our new number will differ from n in the nth digit. That is, for the first number, it differs in the first digit. Again, remember, our first number was 1. Well, cool, and the number we've generated, it's a 2. For our second number, right, its second digit is a 3. Well, cool, the number we generated, it's a 4. For the third digit, for the third number, its third digit's a 5. Cool, our number is a 6. For the fourth, it's a 7. Cool, our number is an 8. Now, what this really means is that, again, for any number, any of the randomly generated reals between 0 and 1 that we've assigned to some natural, right, the number we've generated is going to differ from that number in the digit of the number of the natural we've assigned. So for the first number, it differs in the first digit. From the 97th number, it'll differ in the 97th digit. For the 1037th number, it will differ in the 1037th digit. Go on as far down the naturals as you want. Whatever number you pick, the new number we've generated is guaranteed to differ in the same corresponding digit. Because remember the function we generated to get that diagonal, we picked the diagonal and we added 1 to each digit along the way. So whatever number you pick, whatever point in the list you pick, go across to the digit. Cool. The number we have is guaranteed to differ in that one digit by 1. So no matter what number you pick, we're always going to have generated something that wasn't on the list. And that's really, really, really cool. Because what we've shown by doing this is there's guaranteed to be some number, no matter how long you make that countably infinite list, and try and do that mapping, there's always going to be a real in between 0 and 1 that isn't going to be able to be mapped to a natural number. So by this diagonalization, we know there must be at least one number that wasn't included in our mapping, yet which is a real number between 0 and 1. Consequently, we know there are more real numbers between 0 and 1 than there are naturals. Now, here's the real big kicker. There's a hell of a lot more numbers in R. Because R includes all the reals between 0 and 1, and lots more. All the reals between 1 and 2, all the reals between 2 and 8 billion, And between each one of those naturals, there's going to be more reals than there are natural numbers. So we know that R has a bigger cardinality than N. So if an R-sized number of people showed up to our Hilbert Hotel, ain't no way we can accommodate them, because there's more of them than we got spaces. And that's really cool, because what it proves is that at least one set, so this set of reals, is a non-denumerable set. It cannot be mapped to the naturals. It's a bigger cardinality than countable infinity. So one really neat upshot is there's got to be different degrees of infinity. There's, big, as in mappable to the naturals, and then there's real big, as in mappable to the reals. And that's really neat. So there's lots of really cool things that we can then get from that. So this is just something I thought it's worth sharing. I love this diagonalization argument. I think it's really, really cool. Because again, one really neat upshot is just using some of the basic set theoretic machinery that we've got, we can quickly derive this result that, hey, yeah, there's degrees of infinity, right? This set of things that are just the reals is going to have to be bigger than this set of things that are the naturals. So we get this upshot, infinite sets come in different sizes. So we can use this sort of LF, right? So null here is the cardinality of all denumerably infinite sets. LF1 is a cardinality of a set of all countable ordinal numbers, where an ordinal is a number defining the position of something in a series. 2 to the LFn, or LF0, is the cardinality of the set of reals, so very big number. So there's a lot of debate here about exactly how many kinds of infinity there are. One interesting question is whether there's an infinite number of types of infinity, whether that infinity is itself denumerable or it's non-denumerable. At this point, we get into some really heavy mathematics and some very cool stuff going on here. But I really wanted to introduce you to this idea about diagonalization. Again, this thought about some interesting things that we can play around with once we're thinking about infinity and denumerability and non-denumerability. I think these are really neat results, and so I wanted to share them with you. So cool. Thank you guys for listening. I hope this was fun. So this is really the last kind of stuff that we'll cover. Our next lecture is going to just effectively be a review. I'll give a brief little video talking about the structure of the final, and then also a little brief video talking about, if you're interested in logic, kind of where you might go from here. But really, this is it for our content. So thank you guys very much for participating. Thank you for watching. I hope you've enjoyed it, and I look forward to talking with you again soon. Bye for now.